Okay, welcome to another AQA Physics A-level question, this time on EMF efficiency of a circuit. This is part A and B of the question. Pause the video and read the question if you haven't already. Okay, so I've decided to set up a circuit simulation to try and help explain what EMF is, how you measure it, etc. So here we've got an ideal cell, and it has got a voltage of 9 volts, which means it's providing 9 joules to every coulomb of charge that leaves it. And you've got a 10 ohm resistor and a 10 ohm resistor in series. Okay, and voltage gets shared out in series according to Kirchhoff's second law. So whatever the voltage across the cell is, it must be shared out proportionally to the resistances. So since they're the same resistance, they will get the same share of voltage, so they should get 4.5 volts each. And as you can see, if I get these the right way around anyway, you're getting 4.5 volts across this one, and you're getting 4.5 volts across this one, so they add up to 9 volts. So this is basically a potential divider. If I make this one's resistance greater or less, it will change the voltage across this one in terms of the ratio, right? As long as we've got a 50-50 ratio, we get 50-50 voltage split. If I make this one's resistance less, right, then less energy will be dropped on this resistance and more energy will be dropped on this one. So if I halve it down to 5, okay, so I'm getting a value here of basically 6 volts. So I should then, we know this is still 9 volts, I should be getting a value of 3 volts here for them to add up. Okay, and if I get them the right way around, sorry, 3 volts. Okay, so that works, that makes sense. It also makes sense in terms of the ratios. This is 5 ohms out of a total of 10 plus 5, so 5 ohms out of a total of 15 ohms, that's 1/3, and it's getting 1/3 of the voltage. So all the things we wanted to measure just then, the voltage across the cell, the voltage across this resistance and this resistance, they're all easy to do, okay? But it gets a lot more difficult when the resistance is internal. Okay, so I'm going to make this now have a resistance of 5. Okay, so now when I measure the voltage across here, hold on, did I change it? No, for some reason it didn't change. Right, now when I'm measuring the voltage across this, I'm expecting it to be 9. And what do I get? 6. What's actually happening? Well, I've placed them here, right, but I'm not placing them inside here. We can imagine there being a little resistor, sorry, a little cell and a little resistor, okay? And I am placing the probes here, which is no different from placing them here or here or here. I'm really just measuring the voltage across the external resistance, and I'm getting a value of basically 6 volts. So if I open the switch and now place this on, I'm getting the value for the voltage across what the cell's producing, basically. Okay, the resistance of the voltmeter itself is practically infinite. It's very, very high. So we've got now a new circuit. You can kind of imagine all this being deleted, and we've got a circuit here, and the voltmeter does allow an extremely small trickle of current to flow through it. And since the resistance of the voltmeter is so high, it's nearly all the resistance of the circuit, so you're measuring basically the voltage of the EMF. That's essentially what you're doing. Okay, so if I close the switch again, I'm getting the voltage across the component here. If I open the switch, I'm getting the voltage across, just as though I was taking it across the internal cell, the ideal cell on the inside. Okay, alright, so hopefully that will help us understand the next bit of the question. Okay, so describe how you would make a direct measurement of the EMF of the cell, stating the type of meter you would use. So this is what we were just talking about. Essentially, we are going to place a voltmeter directly across the terminals with no load. Keep the switch open, right? So that means we can just measure the EMF directly. Okay, explain why the meter must have a very high resistance. There's a couple of ways of explaining this, but basically it makes the current very low, so you don't significantly affect the way the circuit behaves. That's what you could say, it's not the greatest explanation, but this is what the mark scheme was really looking for in this answer. And I think these questions are quite tricky. The concept of EMF can be quite tricky, and the mark schemes kind of reflect that by being a little bit more lax in expecting the understanding that I was trying to describe earlier. Okay, so let's move on to the next bit. So again, pause the video and read it if you haven't already. The student is provided with the circuit as below. They want to determine the efficiency of the circuit, and they're looking at the energy dissipated across the external resistor compared to the energy provided, right? So that would be the energy dissipated across the external resistor would be this, the useful power out, and the power in would be whatever was provided by the cell. So we just need to do power out divided by power in. Power out divided by power in. Okay, and the power out will be VI, and the power in will be the EMF times I. Since they're in series, the I's will be the same, so you can cancel them out, and then we can see that that and that are the same. So we've shown that that's how you could calculate the efficiency. Okay, next step. Pause the video, read the question if you haven't already. So now it says add a voltmeter to the diagram and explain how you'd use this new circuit to take readings of EMF and V. So we could place a voltmeter here, okay, and then like we said previously, place a voltmeter of the cell. When the switch is open, you're reading the EMF. When the switch is closed, you're reading the value across the external resistor. Alright, next bit, describe how you obtain a set of readings to investigate the relationship between efficiency and the resistance of the external resistor. State any precautions that you would need to take. So this is only worth 2 marks, but they're asking you to talk about quite a few things. Here the mark scheme was quite clear that you had to say at least 7 readings, right? So you'd replace the external resistor maybe with a variable resistor, or you could use 7 different resistors and switch them out, different values obviously. So if it was with a variable resistor, you would change the resistance, and then you would measure the voltage, right? And since we've already shown previously that you can get the efficiency simply by dividing V by E, E will stay the same. You only need to work out V. You only need to measure V, sorry. Switch the circuit off in between readings so that you don't have current constantly flowing and the circuit getting hot. And also you might want to, when you've switched it off, just check the EMF reading to make sure it hasn't changed, because if it's a cell and it starts to get depleted significantly, it may also affect the EMF reading. Okay, so hopefully this makes sense. Finally, state and explain how you'd expect the efficiency to vary as the value of R increased. Okay, so I would definitely expect the efficiency to increase, alright? But explain why, right? So again, efficiency, we've just seen the formula on the previous page, is power out divided by power in, and power is equal to VI, or you can sub in for V Ohm's law, so you could sub in IR, which gets you P equals I squared R. Okay, so then the power out, right, so efficiency is power out over power in, so the power out would be I squared over R, and the power in would be I squared over the total resistance. Okay, these cancel, so as R increases, this value will become larger, right? So as R increases, the efficiency increases. That's it. Okay, so I hope you found this video helpful. Please like, share and comment. Thanks for watching.